some special properties of these of the websites, the way they link to each other. So if we were to consider PageRank, we have seen the way we can model that with this with matrix and with solving these equations in a recursive way. But there are special cases that we need to consider with our model, and that is the fact that some websites are pretty much dead ends because they don't lead to anything, they don't link to anything else. There are websites that will trap the walkers by not allowing them to go anywhere else and keep them within a trap. And the other things is that if we just do what we did earlier, and if there are these kind of spider traps, they can get a very, very high page rank and have all the walkers end up there and pretty much have a not very good effect on the rest of their page rank for the rest of the pages that are on the web. So because of that, there is a taxation policy that we need to that is being introduced to solve this kind of problem. So the problems that we can encounter, real world problems, is that some pages are dead end. This means the page does not point to any other pages. If that is the case, the page rank that is assigned to this kind of page can leak out. Other type of problems, what I just mentioned, is called a spider trap. When the random walkers end up in a page like that, it has links out, but it has links out to very specific pages that are all part of a same set predetermined group that is designed to keep the web surfers or walkers within those particular pages. And if we have such a structure set up, the way the page rank is computed, it'll get a very high page rank, and it eventually will absorb all of the page rank and have all of the surfers end up in this spider trap. Let's see how that works. If we look back to our example, remember the Microsoft had a link from Amazon pointing to it, but the Microsoft had a link pointing to Amazon. Microsoft had only one link that was pointing to Amazon, and now we have removed that link, and now the Microsoft does not point to anything, and it's become a dead end. So if a random walker ends up in this website, they will have nowhere to go. The thing that changed here is that Microsoft does not have a link to Microsoft, and it's a 0. Does not have a link to Amazon, it's a 0. Does not have a link to Yahoo, it's a 0. You know, before here was a 1, because it did have that link. So if we are to solve the equations change now. We will assign one unit of importance. So what's happening is, what is different here from the previous equation is that for Amazon there was the importance of Amazon was that Yahoo gives it half unit of importance because Yahoo had 2 links. And then there was 1 unit of importance coming from Microsoft. There's a plus M here because Microsoft was pointing to it, but now it doesn't anymore. So Amazon is equal to y over 2, just that. We will start with the vector of all ones we give importance of 1 unit all the pages are equally important. And we will start replacing in the equation, solve the equation. For y, we will get 1/2 plus 1/2, that's 1. For Amazon, we will get 1/2, and for Microsoft, 1/2, because A is 1, so 1/2. Next, we will use these numbers in the equations. So now y is equal to 1. So here we have 1/2, but Amazon is equal to 1/2. So here we have 1/2 over 2. So this will be 1/2. And Microsoft has become a 1/4. Next, we will apply these numbers to the equation, and so on until the numbers don't change anymore. And what you will notice is that they all get a 0 in the end, and the reason that's happening is because all of the surfers end up at Microsoft eventually, and when they end up there, they have nowhere else to go, so it's a dead end. We can see this with the with our graph here. We have Yahoo, Amazon, and Microsoft, and each one gets the same number of random walkers, 10 of them green for Yahoo, red for Amazon, and blue for Microsoft. If we follow our probabilities, Yahoo has 2 links, one link to itself. Half of users are likely to stay at Yahoo, so half of the green ones stay here, and one pointing to Amazon, so half of the green guys will go to Amazon. Amazon only has 1 link to Microsoft. No, Amazon has 2 links, one to Microsoft and one to Yahoo, so half of the Amazon guys go to Yahoo and half to Microsoft. Next, the same thing. So we'll follow the fractions from the equations. So the fractions that we obtained in the second iteration was 1 for Yahoo, 1/2 for Amazon, and 1/2 for Microsoft. So half, well, we can't take the half of 5, so it's like either 3 or 2. But half of the guys will go to Microsoft that were at Amazon, and so on. We will, if we keep applying the numbers from our equation, this is what will happen. You get less and less, as you can see, less and less walkers, because they come to Microsoft, and when they come to Microsoft, they disappear because they have nowhere else to go. This is the dead end problem. Now you will see the spider trap. Here, this is our matrix. The thing that is different here now is that originally Microsoft had a link to Amazon. That was removed. Now we have a link from Microsoft to Microsoft itself. Before, this link was not there. So whatever comes to Microsoft has nowhere else to go, now the walkers. And now when it links to itself, not only that they come to Microsoft, but they have to stay there once they get there, because the only links are to itself. So the difference that you see in this matrix in the previous version was here 0, 0, 0, and now is 0, 0, 1, because Microsoft links to itself. In this case, what changes is this right here. Microsoft has 1/2 link from Amazon, because Amazon has 2 links, and one of it goes to Microsoft, and has 1 unit from itself because it links to itself. So we start with all ones and replace in the equation. For y we have 1, so here we'll have 1/2 plus 1/2, that's 1. And here we will have 1/2, and in the bottom we will have 3/2. Notice now what's happening. What will be the effect of the spider trap? If we keep, we're gonna take these numbers and replace it to solve the equation. If we keep doing this recursively, because Microsoft is a loop to itself, it's going to accumulate now all of the walkers on its website. So the next time we'll get 3/4, 1/2, 7/4. Then this becomes 2, and eventually 3. And the other websites have 0. So that's what we mean by a spider trap, that this website will get all of the web surfers on itself, and the rest of the websites will get no web surfers or no walkers. So if we see this with the picture, again we start with 10 random walkers on each website, and if we apply the probabilities of the numbers from the equation, half the Yahoo guys go with Amazon, and all of the half the Amazon guys go to Microsoft, but all of the Microsoft guys stay there because there is a loop to itself, and they have to stay there. They have nowhere else to go. In the next iteration, the Microsoft gets some of the again half the Amazon guys, which originally came from Yahoo. These are the green ones, and eventually Microsoft gets all of the walkers, and the other websites have no walkers. This is when we got the 3 we got the number 3 in the equation. So we have 0 for Amazon, 0 for Yahoo, and 3 units of importance for Microsoft, which is all of them. So we got all of the walkers when we converge with this iterative PageRank solution. So this is called a spider trap. How are we going to design the PageRank so that it can avoid this kind of problems, dead ends and spider traps? So what we can do is introduce the notion of a tax. So we will still compute the importance of each web page according to the number of pages that link to it. However, we will tax a page a certain percentage of each iteration. So as we are solving our equation to reach the limit, we will multiply by some constant, and this will be tax. So we will add a fixed constant of tax to all pages. In this case, if we have this spider trap, the Microsoft will still get a lot of walkers, and it will still get a high page rank, but it will not get all of them, because we are adding this some percentage of tax here in the computation. So the way we model this is we assume a fixed probability of leaving the system and a fixed number of walkers injected into the system at each step. This tax is the same for all of the pages that we are computing the page rank for. So this will be divided equally among all the pages. If we can assume, let's say, that the tax is 20%. So what happens is the original page rank is some number, some unit of information, and we will only get 80% of that. 20% is taxed. So we will multiply this page rank computation by this 0.8 factor because 20% is taxed away. And then we can add this fixed number to all of them. If that is the case, and the Microsoft is still a spider trap, this was our original equation, was A over 2 plus M, and that's when the Microsoft got all of the walkers and all of the page rank and all the importance, and the other two websites got 0. But now if we introduce this tax, this is what happens. We will try to solve the equations with 1 for Yahoo, 1 for Amazon, 1 for Microsoft, all of them equally important. If we do that with 0.8 plus 0. Multiplying by the 0.8 factor, then Yahoo will get 1, Amazon 0.6, and Microsoft 1.4. Microsoft is still a spider trap. It will continue to grow. The thing is that next we will use these numbers in the equation to solve the equation. Next we'll use these numbers to solve the equation until we converge. And when we converge, this is what happens. Microsoft still got the highest importance because of the spider trap. However, the other pages don't have a 0 anymore. They retain the sum of their page rank. Another way to solve that is if we consider the semantics of the pages. In other words,